That's the new theme song for the day. And today we are going to continue to be talking about acid derivatives. All right, and we are talking about the anhydride today. Quick reminder, here is the structure of the anhydride. It is 2 carbonyls with 1 oxygen in between them. What this means is, in terms of leaving group ability, assuming the anhydride is symmetric, and 95% of the time people are going to be using symmetric anhydrides, what this means is, generally speaking, when a nucleophile comes into play, let's say this one right here, and attacks one of those carbonyl carbons, the group that leaves is 1/2 of the molecule, like so. So your product looks like this. Your product looks like this. The major organic product is considered to be this, while this is the byproduct. Okay, does this look that different from the acid chloride reaction that we talked about earlier? Honestly, no, it's not that different at all. So there are only a couple ways of making anhydrides. I'm going to remind you of the one we just talked about, which is going from acid chlorides to anhydrides. And that is, you react the acid chloride with the carboxylate salt from a carboxylate salt that's usually identical to the acid chloride, and you make this. Now, I've gotten a couple of questions from some people, and the question was this: could you do this? Could you do this reaction? I don't know if in place of, I think it was more of a general, will this work? And that looks like this. Can you use the carboxylic acid instead? The answer to that is yes, you can, but there's a reason we don't want to. And that reason is right here. This is the reason right here. So folks, what I want you to notice here is with the salt product up here, there's no spare proton you have to worry about. But down here, you've got that proton you have to worry about, how to get rid of it. Now, it's not particularly hard. You could be doing this in pyridine. That would certainly not be completely out of the question. You could also be doing this with a little bit of atmospheric water involved. Either way, you got to lose that H+. And so you wind up with the anhydride. Is one of these better than the other? Personally, I prefer that version. Wow, yellow just really doesn't show up. I won't do that again. I prefer using the carboxylate salt, principally because you don't have to worry about that hydrogen chloride afterwards. Now, there's another way that is probably the most common way of making anhydrides. When people get anhydrides, they either make it this way or they buy them. And ladies and gentlemen, I always recommend you buy them rather than try to make things. My research advisor when I was in graduate school had this comment once. Someone asked him, how far back should we start our syntheses with, like what starting materials can we use? And he paused and he said in his very cultured Southern accent, he said, I suppose in theory you should go back to earth, air, water, and fire, but I like to open up a catalog and see how close I can get. So the other way that we can make anhydrides is like so. You start with the carboxylic acid and you react it with P2O5, phosphorus pentoxide. And the product is your anhydride. You cannot make asymmetric anhydrides this way. You just can't do it. What you would end up with if you use two different carboxylic acids is a mixture of 3 different types of anhydrides. And that's no fun for anybody. I'm not going to hammer you for a mechanism on this because I really don't think it's that important. The only thing I do want to point out is that P2O5 is incredibly dangerous. It reacts violently. I mean, practically nuclear warhead exchange violently when exposed to water. Now, I've never set anything on fire this way myself, but I know a couple people who have, and they'll tell you it's a nasty, nasty damn thing. Now, that's pretty much the 2 ways we have of making an anhydride. There's one more I'm going to show you, and I'll do it on this page, although I don't really expect you to be responsible for this. I think it's kind of cool, and let's face it, you're taking my class. So, if I think it's cool, you have to hear about it. This molecule is called phthalic acid. All right, it's naturally occurring. What you do is you heat the bejesus out of this. You heat the bejesus out of this thing, and what you get is the anhydride plus water. This is not commonly done, and it only really works in this one situation. I just thought it was kind of cool, and I wanted to show it to you. All right, so reactions of anhydrides. Reactions of anhydrides. Remember, we can only go down that list. So this reaction is not even remotely possible. That's not going to happen because you cannot go up in energy. So what you can do, though, is you can turn this into an ester, a carboxylic acid, an amide, and finally, the salt. All of these are possible. So let's go ahead and plow through some of these. Remember when I said yesterday or last time you were watching this video when we were talking about acid chlorides, and you never have to pole start an acid chloride for a nucleophilic carbonyl reaction to occur? Well, most of the time, you don't have to with anhydrides either. So we're going to use this as our anhydride. And our random nucleophile is going to come in and attack. Knock the group off, and we make this. With the carboxylate salt as the byproduct. Easy peasy, Ginny Weasley. That's how this one works. So, in almost every case. So let's say you want to make an ester. Your options are react the anhydride with methoxide. React the anhydride with the alkoxide. Bam, bam, and you get this. Now, I want you to note, in both of these cases, the generic one and this one, we've gone ahead and generated the salt on both of these. So we really don't have to spend a lot of time worrying about that salt itself. So now another question would be, could you use this? Sorry about that pause there, ladies and gentlemen. My son just walked in and wanted to show me his new haircut he got. So this method works. Now, I will say that anhydrides do react much more slowly than acid chlorides do. In fact, the next video we're going to do is talking about those leaving groups. So I'm already over 10 minutes, so let's skedaddle just a touch. How would we go from an anhydride to, say, the carboxylic acid? And I just gave the answer away. You would react it with water. Or you could react it with sodium hydroxide if you wanted to. So this is how we go from anhydride to acid. Remember, all of the derivatives can be transformed back into the parent acid in one step. So the last one we're going to talk about right now are these, how you make an amide. And like with the acid chloride, the best way to make an amide using these things is take an amine, but you need two equivalents of it. You need two equivalents of that amine. So the product here would be the amide and, oh, sorry, not the salt, my bad. The amide and the acid. All right. Mechanism for this. It's exactly the same as the ones that we have been doing, so I'm not going to belabor the point with it anymore. Work your way through it. If you get stuck or you have some questions, feel free to ask me. I'm watching the clock here because I can't go over 15 minutes. The final thing I want to say about this is you could use two equivalents of a secondary amine, and the product you would then get would look like this. I'm sorry, not H, would look like this. All right? So the type of amide you make is directly related to the kind of amine you use in this reaction. All right, folks, that is the end of the anhydride section. So I'll see you the next time we talk.